So in that last situation, let's see if I can get that set up again. There we go. There's a point somewhere in the middle that's not moving much. It's not consistent there. That, and then her hand also is not moving at all. And then in theory, my hand's not moving, but in reality I have to move it some. The points which don't move are called nodes. The points which move a great deal that are swinging back and forth are called antinodes. So, and the pattern that you're seeing set up there is known as a standing wave. Now, I'll demonstrate in the classroom with string and a string vibrator, and it'll be potentially much clearer. And what type of waves was that?
Transfers.
There we go. All right.
Now, which one is that? The parallel, or is it perpendicular?
Perpendicular.
How is that perpendicular? Can you actually explain that? I have a hard time understanding this.
Because he was going like this, and then I was just going like this.
Oh.
They're both transverse waves.
Yeah.
A transverse wave, it's because the coil themselves are just moving. When she did it up and down, and when I did it side to side. But the wave is going this way or this way. So that's a transverse wave because this coil right here isn't moving this way much at all. It's moving back and forth.
So it's like moving opposite of the direction of the wave.
So what would be a parallel, like the other one? I don't know.
Longitudinal?
Yeah, the longitudinal is hard to do on this one.
Oh, so
That-
you're just...
That's sort of longitudinal, sort of. Because the particles are moving with the wave or opposite the wave.
So you're sort of pushing the spring closer together when it's longitudinal?
Yes. Just like with sound, you push air molecules closer to the next air molecules. And then they tell two friends, and they tell two friends. All right, so when I created the standing wave, it's known as a standing wave. It's also known as a harmonic. That's the second harmonic. The first harmonic is, in theory, the simplest one. Harder to do on the floor. That would be a first harmonic where you've got a node at her end, in theory a node at my end, and then a big antinode in the middle. Second harmonic. Oops. Now I'll go for third harmonic. That third or fourth? How many antinodes are there?
It's busting my knuckles open.
What's that?
I said, whatever it is, it's busting my knuckles open.
Oh, sorry about that. Okay. Besides your knuckles being busted open, do you need to stop?
No, it's all right. I just changed my hands. I didn't know you ain't prepared me for the fourth wave. No, the third
Your
or
mind reading
fourth.
skills aren't working today either.
Huh?
Your mind reading skills aren't working today either.
Happened to me today. I don't know.
You need to put that in requirements. All right. All right. So that was the third harmonic with the three antinodes. Now you can't always say, oh, how many antinodes? Okay, that's the harmonic it is. That works for two fixed ends. It doesn't work for some of the other patterns. All right. And then fourth harmonic. I'm about to go faster.
I got it that time.
It's either fourth or fifth. I can't quite.
I think it's fourth.
Okay, we'll go with fourth. And
Well,
apparently I
they
can't
got-
do fifth right now.
I was say because it looked a little funny. Like some of it was a little bigger, and then part of it was.
Yeah, that's me. All right. Now I can alter it. I was changing the frequency in order to get to the new harmonic, and potentially I can change it a different way by tightening it up. Please don't let go.
Okay.
So think about, sort of picture how fast the wave was traveling before. Now picture how fast it's traveling. So faster or slower?
Faster.
Because in a transverse wave, as this particle starts moving out this way, it's pulling the ones next to it. Well, that pulling force that one coil has on the next one is tension. So by increasing the tension in this, each coil is pulling harder on the next one, allowing the wave to travel faster. So I've got wave like that, we're tightening it up. And so I can create, with the wave moving faster, I don't have to move my hand quite as fast. I think that's third.
Oh, that's so cute. See, because I'm loosening up my body, mister. I'm becoming jiggly, so you moving that in me.
I'm sorry, or you're welcome, I'm not sure. All right.
You know what they say? Sorry.
What did they say?
I think I've covered what I wanted to cover with this, so let's head back into the classroom.
Shut up, I was just joking, guys. I was-
You didn't see your name?
I just saw like somebody named Matt and Carrie. Maybe it's because it's on my phone.
All right.
I better
Just-
look on my computer.
Jancy, did you ever figure out what the issue was?
I just looked at the PDF that you sent me in the email. I couldn't find it
Yeah,
online.
because
for
on
you.
mine
I'm
it's
sure it's there.
somebody named like Carrie, Matt, my name's not even on it.
All right, because Jancy also had that issue where he wasn't seeing his name. Anyone else? You
There are
also
two
couldn't find
different
your name?
PDFs.
Pardon?
There's two different PDFs.
I only saw the one.
There's one on the, there's one on the home page. If you scroll down to the bottom of like that sidebar thing,
Uh-huh.
there's like, coursework on like the very bottom of the page, like sidebar.
So there's
whatever.
two things called coursework?
I thought that was.
Yeah,
what I
there's a,
said.
there's a PDF in there,
In the coursework, what's your name?
but it's for the wrong,
Erica.
it's for the wrong people.
Yeah, you're on here. How did you get there? Cause I can't find it. Mine, I went to the assignment one and then.
It's not under assignments, it's under coursework.
You go
Oh,
under
okay.
coursework, pick 11 through 14, scroll down until,
This is the coursework.
yeah, so, yeah, just do it. Coursework.
Maybe it's for your.
So I've got something called assignments.
It's probably for your online class or something.
Oh, and then it will be there. Oh, cool. Okay, thank you. What is that? Is that like chapter 11?
Oh, chapter 11, question 44.
So what is on the test is, what chapters are we gonna be finishing up today?
It'll be 15 through 21.
Those are the ones that will be on the test?
Yep.
Yeah, yes,
So what is this measuring, sound?
Say again?
So what is this measuring, sound?
No, this is string vibrator. All right, so this is vibrating up and down. I don't know if you can see it. I think you can hear that because it bangs against my fingernail. So this thing's oscillating up and down at 60 hertz, which means 60 times a second it's going up and down. I think for these purposes. I'm assuming you did not do this lab. All right, so we'll turn this on. And so by adjusting the tension in the string, I can change the harmonic. So I got, you can sort of see it right there. My hand's shaking a little bit, so it won't be perfect. But we got, quiet. There's, there, that one's looking better. So I have a, stop. All right, so I've got an anti-node here. If I can keep my hand steady. There's a node here, anti-node, better sometimes than others. Node, anti-node. So 1, 2, 3, 4, 5, 6, 7 antinodes. Seventh harmonic. As I increase the tension in it, 2, 3, 4, 5, 6, sixth harmonic. Increase tension even more. Come on, don't fail me now. Fourth harmonic. I assume you can see it. Sometimes there's background issues. Looks like that thing's about to come snapping. All right, wasn't timed particularly well. So in the lab piece of it, you change the tension in the string here, and you get different harmonics, and then from that you can actually predict what the frequency of the vibrator is. So one of the other factors, we talked about the frequency affecting it out there, and we've talked about the speed of it, and the fact that there's increasing the tension increases the speed. Now we can do a little bit better than that. There's a generic formula for speed of a wave. I'm not going to derive it, I'm sort of present it. Thank you. It's a square root of, there's going to be some force term and divided by some inertial term. In other words, the force term is how much does moving one particle affect the next one. The greater the force, in other words, in the case of the coil, the greater the tension, we have a greater force being applied to the next one. And that is the word force. And the inertial term is how much mass am I actually trying to move. The greater the mass is, the harder it is to move it, or to get it to change whatever it's doing. So in the case of the string, so basically a one-dimensional medium is specifically the tension divided by,
Is that a 1D? Right, that D?
1D for one-dimensional. I'm basically can consider the string one-dimensional. This one, the mu on the bottom, this Greek letter mu, this is for linear density. It's the same symbol we use for coefficient of friction, but it stands for linear density here. So what's the formula for density? Just the plain old everyday density.
I think it's like volume over.
It's something over volume.
I can't remember. I think it's.
Not pressure.
Mass over volume?
Mass over volume. So regular density is mass divided by volume. Surface density mass divided by area. Linear density. Someone take a shot at it?
What was it?
Divided.
So regular density, mass divided by volume. Surface density, mass divided by area. Linear density,
Mass divided by height.
length.
I was thinking like, okay.
What's that next to the V? Yeah.
Here, it's 1D for one dimensional.
Okay, is that velocity, the V?
Yeah, the speed. Let's start this tonight. Yeah. So if I took a piece of string, so in essence, in the lab, you take a long piece of string because string doesn't really have much of a mass to it. So making up numbers, if I have 3 meters of string, and which has a mass, so my length is 3 meters, and which has a mass of 4 grams. So I have my string attached to the string vibrator. At the other end of the string, instead of just holding it, you have it dangling over a pulley. This is the pulley. And at the end of it, you put 2 kilogram mass. We can figure out how fast the wave is actually traveling along the string. So, if this mass here is just hanging there in static equilibrium, then the total force acting on the mass would be 0. Well, I have weight acting down, I have tension acting up. What is the weight of a 2 kilogram mass? Or how would you find it?
Would be mass divided by.
Mass times 9.8,
What times 9.8?
the mass.
Mass, okay. Yeah. So you multiply, so the weight is 2 times 9.8 or 19.6 units.
Yeah, yeah.
So if this is in equilibrium, then the tension would also have to be equal to 19.6 newtons. So I know tension now. The linear density is just mass divided by length, and I've got my mass, I got my length there.
Oh, is that what the N is? That's linear density?
With this,
Yeah.
the mu, it's the linear density.
Okay.
Sometimes the symbol lambda is used. Sometimes that's used instead. Just like for surface density, sometimes, no, that's an epsilon, there's a, oh, that's right. And eta is sometimes used for surface density. All right, so we can find the linear density because I have mass divided by length. Now the trick here is that if we use triple beam balances, it would tell us it in grams. But we have length in meters, we have tension in newtons. If I want to make sure I get meters per second here, I need to, what units do I need for mass?
What was the question?
If my tension is in newtons, my length is in meters, and I want meters per second for my speed, what units does my mass need to be in?
Kilograms? Kilograms?
Yes. So 0.004 kilograms. And so my linear density, 0.004 divided by 3. .00133 repeating.
And we just found the, okay.
Linear density. So it's saying that every meter of string has a mass of 0.00133 kilograms.
And you said you just found the linear density.
Yes, linear density.
And the 19.6 is the surface density?
No, the 19.6 is the tension.
Okay, oh, SE equals the 10, okay.
So,
And you got that by, multiplying 2 times 920,
yes,
okay.
so this becomes 19.6 divided by 0.0013. That's newtons on top and kilograms per meter on bottom. Give a little bit of room here.
He wants to tell you that?
Yes, please.
Oh, I don't know if it's right, but I got like, so I know, 15076.
15076. I assume that's before you take the square root?
Oh, I didn't see that. Let me see that.
121?
I got 122.7.
So somewhere in that range. 121 to 122. In units,
Kilograms, I mean.
Meters per second.
yes,
Is it squared or just meters per second?
just meters per second.
And what is the V1D again? D stands for what?
The speed, one-dimensional.
One dimensional.
So if I have something that is, the length is so much bigger than how thick it is, considering the number of people have asked already, so this is one-dimensional.
Why didn't I comprehend that V was for speed?
I didn't either.
I don't know. Because V is for vendetta.
Yeah, you got it out for us, cause you didn't tell us it was V.
It's cause you're always trying to trick us.
No, we do know V is for, for speed, we do know that, but I guess for this case, I didn't comprehend that would have been speed.